Embeddings are numerical representations of data, like words, images, or tokens, that capture their meaning or relationships. They turn something symbolic, like a word, into numbers a machine can understand. Neural networks often include embedding layers within the network architecture. These receive processed data from preceding layers and have a set number of neurons that define the dimensionality of the embedding space. Initially, the weights within the embedding layer are initialized randomly and then updated through techniques like backpropagation. These weights initially serve as the embeddings themselves, and then they gradually evolve during training to encode meaningful relationships between input data points. As the network continues to learn, these embeddings become increasingly refined representations of data. Instead of treating words as simple, discrete units, like assigning each word a unique number, embeddings represent words and other pieces of text as numerical vectors. Imagine you have a vocabulary of thousands or millions of words. If you just gave each word a number, say cat is 1 and dog is 2, the model wouldn't have any inherent information about the relationship between these words. They would just be different numbers. Embeddings change this. Word embeddings map words into a multidimensional space where related words are placed closer together. For example, the embedding vectors for cat and dog might be numerically closer to each other than the vectors for cat and banana, because cats and dogs are both animals. This means that the numerical representation itself carries information about the meaning and relationships of words. This idea was a significant development in NLP, moving away from treating words as discrete symbols towards representing them in a continuous space. In transformer models, which are the basis of modern LLMs, the input text sequence of tokens, words or parts of words, is first converted into a sequence of embeddings. These input embeddings are more than just simple word representations. For each token in the sequence, the input embedding is typically a combination of several pieces of information represented numerically. Token embedding. This is the core representation of the word itself, carrying information about its meaning and linguistic properties as learned from the training data. Positional embedding. Neural networks don't naturally know the order of words. Positional embeddings tell the model where each token appears in a sentence, first, second, third, etc. Without them, the model wouldn't know the difference between dog bites man and man bites dog. Segment embeddings sometimes. If the input consists of multiple segments, like 2 sentences for a task that requires understanding their relationship, segment embeddings can be added to indicate which segment each token belongs to. By combining these embeddings, each token in the input sequence is represented by a single vector that captures not only the token's meaning, but also its position and context within the input. These vectors are then processed layer by layer throughout the transformer network. As the data flows through the transformer layers, the model generates new sets of vectors at each layer. These vectors are often referred to as contextual representations or hidden states, as they represent the words in the sequence, but now incorporating the context learned through the processing layers. The output of the final layer is the model's most refined numerical representation of the input sequence, which is then used for the final prediction task, like determining the next token. Even the concept of soft prompts used in some advanced prompting techniques relates to embeddings. While traditional hard prompts are sequences of natural language text, soft prompts can be thought of as hidden, distributed representations, essentially learnable vectors embedded within the model's input or layers that guide its behavior without being explicit text. This shows how numerical representations beyond just word embeddings are fundamental to how LLMs function and are controlled. In essence, embeddings are the language of neural networks for text. They transform words and positional information into numerical vectors that models can process, allowing them to understand relationships, capture meaning, and ultimately generate coherent and contextually relevant text.